This is section 1.3, Evaluating Limits Analytically. We have three objectives for this section, which is to evaluate a limit using properties of limits, then to look at other ways of evaluating limits when those properties don't work, such as dividing out and rationalizing, and then to look at the squeeze theorem. So first let's talk about properties of limits. Limits is going to be a recurring theme for the first half of the course. Keep in mind that direct substitution is the best way to go. So if we're able to take the function, in this case the limit as x approaches 3, and simply plug 3 in every time we see an x and evaluate the expression, that's ideal. So in this case, the limit as x approaches 3 would be -1. Now obviously that's a perfect scenario where we're able to plug it in, and sometimes you will be able to and sometimes you won't. So we're going to develop over the next several lessons ways to find limits using some different properties. So here are some basic limits. Again, the first one says if you are taking the limit, and it really doesn't matter what c is, if you're taking the limit of a constant, the solution is that constant. So our first example here, the limit as x approaches 3 of 5 is 5. And if you think about this, really we're just looking at a graph of a function, and that graph is the function y equals 5. And so it looks like this. So it doesn't matter as x approaches what, we know the solution will be 5. Same thing if it's the limit of x as x approaches c. Again, it's kind of like direct substitution. I'm basically just plugging that 3 in to get a 3. And same thing here, this is just a direct substitution. If I have the limit as x approaches some value of x to the n, the solution is c to the n. So this would be 3 squared, which of course is 9. So the second two are direct substitution. The first one is just a property that you need to remember. Let's look at a few other properties. Here we're dealing with a limit as x approaches c of f of x is L, a limit of x approaches c of g of x is k. So there's some different properties that you're going to want to know. The first is scalar multiple. And essentially what we're doing is we're thinking about the fact that if we have some constant that we're multiplying by our function, so say I had 2 times the quantity of x plus 1, I can take that 2 and pop it to the front, go ahead and find the limit of f of x and take it times the 2. Sum or difference, same idea. If I have two separate functions, I can just find the limit of each function and then add or subtract it. Same thing for multiplication. Same thing for division, assuming of course that k is not 0 because we don't want to divide by 0. And the last is the power. So if you have the limit of a function to a certain power, you can go ahead and find the limit, replace it with the limit, and then take it to whatever the power is. So here's an example of how we might use some of these properties when finding a limit. So notice here I'm trying to find the limit as x approaches 2 of 4x squared plus 3. And yes, I could just take the 2, plug it directly in, and that is what I would do typically in this situation. But I'm going to go ahead and do it sort of the long way so you can see how it breaks down. So I can break it down into the sum of two different functions, and notice I'm finding the limit of each function. I'm using that scalar multiple rule that says if you have a 4 here, you can take it to the outside. So that's what I've done on this step. Now I'm just doing some direct substitution. This is using that power rule. So 4 times 2 squared, so it's direct substitution, but it's also the power rule. And then I'm combining my values, simplifying. So would I ever typically do it in this fashion? No, of course not. It's just a lot of extra work, but it's important to see what those properties will do for you. Always a good idea as we're working on this to keep in mind that we can take a look at what the function looks like. And in this case, we're dealing just with a polynomial. And so we know in this case, because it's a quadratic, it's going to be a parabola. So it would make sense that the point 2, 19 would be a point on our parabola. And again, this just reiterates that we don't have to go through the rigmarole that I took you through using the properties. We can use direct substitution, take 2, plug it in for x into our function, and we still get 19, so that's just called the direct substitution. So always do that first if you can. Notice it says this works for all polynomials. It works for all polynomials because we don't have any restrictions on our domain for polynomials. It works for rational functions too, assuming that it doesn't make our denominator 0. Here are a couple of limits of polynomial functions. I didn't include a rational here, but limits of polynomial functions, go ahead and try both of them and then press play to see how you did. So again, if possible, and here it does seem to be possible, we're just going to use direct substitution. So I'm not going to use all of my properties to break this up. I'm just going to say the limit as x approaches 2 is, or of f of x, we'll just call it f of x, is 3 times 2 cubed minus 2 plus 2. So 2 cubed is 8 minus 2 plus 2, and that gives me 24 minus 2 plus 2, which is just 24. For the second one, again, I'm plugging in 2. I'm going to use direct substitution because there's no reason why I shouldn't. So I'll get 2 plus 1, which is 3, and then 2 plus 2, which is 4 squared. You're in calculus, so I know that you know the order of operations. We're going to take 4 squared to get 16. 3 times 16 is 48, and we're all done with that question. Here's another limit. This one's involving radicals, but again, don't make things more complicated than they need to be. The limit as x approaches 2 of radical x plus 4, if I can use direct substitution, which I can in this case, oops, got ahead of myself, then that's what I'm going to do. So I'm just replacing x with 2 to get a final answer of x, or the limit as x approaches 2 of that function is radical 6. This is going to work for direct substitution, assuming that c is greater than 0, which means we want the radicand to be greater than 0. So now let's talk about the composition of functions. We of course have composed functions before in other courses. This is talking about limits instead, but it's really the same concept. We're just dealing with limits instead of the actual function. So first let's take a look at the limit as x approaches 2 of f of x. So as x approaches 2 for f of x, I can use direct substitution to find negative 2. Now, again, I'm leading up to that last one, so for now, I'm just going to plug in, find the limit as x approaches negative 2 of g of x, and that's going to give me, again, by direct substitution, negative 8. So here's where the composition comes into play. I've got the limit as x approaches 2 of g of f of 2. Now, as always with composition of functions, we start here. And really, this should say g of f of x. So we're really finding the limit as x approaches 2 first of f of x. And that limit, as we already determined, was negative 2. So essentially what that's telling me to do is at the next step, I'm saying find the limit as x approaches negative 2 of g of x. Again, why negative 2? Because this the limit of f of x as x approaches 2 is negative 2. So that becomes our new limit. And now I'm taking the limit as x approaches negative 2 of g of x, which we've already determined is negative 8. So that is how composition of functions with limits works. You're just using it with the limits instead of the function itself. Limits of trig functions. The great thing, again, starting here, is if you can use direct substitution, notice that my property tells us if I'm taking the limit of sine of x, it's just sine of c, or cotangent of x, it's cotangent of c. So again, make sure you have your unit circles out, be ready to go with this. When I'm finding the limit as x approaches 1 of sine of pi x over 2, really I'm finding sine of pi times 1, which is just pi, over 2. And so sine of pi over 2 is 1. If I'm trying to find the limit as x approaches 2 pi of cosine of x, again, I'm just going to do direct substitution and find the cosine of 2 pi. Cosine of 2 pi is 1, so that is my solution.